Hey everyone. So, we all know LEDs, right? I mean, they're everywhere. Those awesome little gadgets that gobble up electricity and spit out light.
Yeah, it's a super familiar idea. But have you ever just stopped and thought, what is the opposite? Is there some kind of component that can catch light and turn it back into electricity?
Well, you bet there is, and this slide nails the comparison. You've got your LED turning electricity into light. And then you have its mirror image, the photodiode, which takes light and turns it into electricity. And that's exactly what we're going to dive into today.
All right, let's get right to it. What is a photodiode officially? Let's get the proper definition down.
And here it is, the textbook definition. At its core, a photodiode is just a semiconductor that converts light energy into electrical current. Think of it as a tiny energy translator, changing photons, light particles, into a flow of electrons we can actually do something with.
Okay, now this next point is super important. This is the secret sauce. A photodiode has to operate in what's called reverse bias. Now, what does that mean? Basically, we're hooking it up backwards on purpose. This stops the normal flow of current and creates this perfect sensitive state just waiting to detect light. Seriously, remember that term, reverse bias. It is the key to everything.
So, we know what it does, but how are they actually built? Let's peel back the layers and check out the anatomy of this little light catcher.
But before we get into the nuts and bolts, we got to talk about the science behind it. The whole thing works because of a principle called the photoelectric effect. This is just an incredible idea where when light hits the right material, it literally knocks electrons loose. It's like a tiny game of pool, where a photon is the cue ball hitting an electron. That's the engine that makes this whole thing go.
So how do you actually use that effect? Well, the construction is actually pretty simple. You take a standard PN junction diode, a really common electronics component, and you just make one key change. You give it a little window, a transparent opening so that light can get inside to where the magic happens.
And this lays out those key parts perfectly. So at its heart, it's a PN junction diode. That's what gives it that special light-sensitive area. Right at that junction, you get what's called a depletion region. We'll get to why that's important in a sec. And of course, it's all wrapped in a clear covering to protect it, while still letting those light photons get in. Okay, so we know what it is. We know how it's built. Now for the big question, how does it actually work? Let's follow a single particle of light, a photon, on its journey to becoming electricity. It really breaks down into 5 simple steps. First, we apply that reverse bias we talked about. Remember, hooking it up backwards. This creates a really wide, sensitive depletion region. Step 2, light, made of photons, streams through that window and hits the junction. Then step 3, those photons smack into the material and create what we call electron hole pairs. They basically free an electron, leaving a little positively charged gap or a hole. Step 4 is where the reverse bias comes in. The electric field it creates acts like a super strong magnet, grabbing those pairs and ripping them apart, pulling electrons one way and the holes the other. And finally, step 5, that organized movement of electrons is, you guessed it, an electrical current. It flows out into the circuit for us to use. And that special current that only exists because of light, it has a pretty straightforward name. We call it the photocurrent. Make sense, right? Current from photons? Okay, that's the theory. But let's bring this into the real world. How do these things actually perform, and where would you even find one? So here's a weird little detail. Even if you put a photodiode in total darkness, like pitch black, a tiny bit of current still leaks through. This little trickle of electricity is called the dark current.
And this chart shows the whole story. See that first bar? That's your tiny little dark current when there's no light. But look what happens when you add a little light? The current goes up. And when you add a lot of light, the current goes way up. It's a really simple relationship. The brighter the light, the more current you get. Super predictable.
So why do we care? Because this simple device is literally everywhere. It's in the fiber optic cables that bring you the internet. It's the light sensor in your phone that adjusts the screen brightness. It's the little eye in your TV that catches the signal from your remote control. It's even in smoke detectors and super precise medical gear. They're just all over the place.
All right, that was a lot, I know. So let's wrap it all up with a simple framework. This is your cheat sheet for explaining a photodiode to anyone. If you ever need to explain this, just follow these steps. 1. Give the definition. 2. Talk about the construction. 3. Explain the core principle, that photoelectric effect. 4. Walk through how it's working. 5. Cover its characteristics, like photocurrent and dark current. And 6. Finish up with all those cool applications. Follow that roadmap, and you've got it down cold.
And there you have it, the photodiode.
A really elegant way to turn light into an electrical signal. Kind of makes you wonder, right? Now that you know how we can translate light into electricity, what other amazing technologies out there are using the same powerful effect, maybe in ways we don't even realize? That's something to think about. Thanks so much for joining me.